Let me finish this part C of question 5 first. Now, why did I just point this out? Because it's kind of not important. The intersection, the y coordinates of the intersection of the normal. So what do we actually need to do? Now, part C gives us a very important additional condition. That is, if PQ is a focal chord. If PQ is a focal chord, that means since PQ is a focal chord, little p, therefore little p times little q is -1. That is, therefore, the x coordinates of your intersection of normal becomes this. And of course, your y coordinates is something that I just pointed it out. And therefore, your u becomes a brackets p plus q and something like this, which is variable. Something varying depends on the values of p and q. Now, if you record it, the intersection of the two tangent has a coordinate of this in APQ. And if you can realize that R and U now, they have the same x coordinates. In other words, no matter where R is and U is, they are always on top or below each other. That means R and U is a vertical interval. Since R and U have the same x coordinates, therefore RU is parallel to the x-axis, or to the y-axis, sorry, parallel to the axis of the parabola, which is the y-axis in this case. Okay, so that concludes the end of question 5. Now, next part of the lesson, we are going to move on to the Cartesian approach of tangents and normal to the parabola. Approach oops, right wrong. Tangents and normals to a parabola, and it is the Cartesian approach. We did parametric approach before. This time we do Cartesian approach. Oops, that's so dark. Okay, so what does that mean? This means we no longer have 2ap squared. We have the parabola x equals 4ay, x squared equals 4ay, and this time my variable point p called x1, y1. So normal parabola concaving up with this time p is x1, y1. Now we just use our knowledge in derivative in order to find out what the gradient of the tangent is at this point, and then use point gradient formula to work out what the equation of the tangent is. So first of all, in order to find out the derivative, we want to make y the subject, which is x squared equals 4a. I emphasize I didn't do this in the parametric approach because it's for the Cartesian approach. So dy dx equals to 2x on 4a, which is x over 2a. And don't forget, this is a derivative function. We need to find out the actual gradient at this specific point. So therefore, at x equals to x1, derivative equals to x1 over 2a. So therefore, in other words, the gradient of the tangent is x1 over 2a, not just x over 2a, because x1 is in fact the x coordinates of your point P. So therefore, the equation of the tangent Now, to derive the equation of the tangent, there's a little trick inside here, which you always need to memorize. Let's take a look. So that's easy, just y minus y1 equals to x1 over 2a, x minus x1. Now, and then easily we just multiply, because we want to get rid of a fraction, we multiply both sides by 2a. Be careful which one is y1, which one is y. It's easy to actually get confused. Now, before I continue, I will tell you the result. The result we want to get to the end is that the equation of the tangent in Cartesian form is x(x1) equals to 2a brackets y plus y1. That's what we're trying to achieve. But in fact, in this case, it's not quite there yet. So we would like to use some trick in order to actually make it look like that and see how we go. So that is 2ay1 equals to x(x1) minus x1 squared. It's pretty close. We got this term. But these two are not quite the same as this, especially in the one that we want, we don't have x1 squared term. So now we're going to use a little trick. Since point P, let's restate this, lies on the parabola. Point P is a point on the parabola. That means your x and y coordinates definitely satisfy your original parabola equation, which is x squared equals 4ay. That is, therefore, x1 squared equals 4ay1. I simply substitute the x and y coordinates of point P back into the parabola equations. So therefore, in this case, if x1 squared equals 4ay1, I can replace this x1 squared by 4ay1. So therefore, the tangent equation becomes 2ay minus 2ay1 equals xx1 minus 4ay1. And now the questions just ask us to make xx1 on one side. Now I move this part to the right hand side. That will give us, minus become plus, 2ay plus 2ay1 equals to xx1. By taking that 2a out, we got exactly what we need. Therefore, the tangent is tangent equation at P is xx1 equals to 2a brackets y plus y1, where again, point P is a point on the parabola. This is very, very important because we are going to deal with that a point that it's not on the parabola and get a very, very similar result in the next lesson when we derive the equation of the chord of contact. Okay, so this is the equation of the tangent. Again, it is on the formula sheet. All you need to do is to identify what A is, what your point on the parabola is, in order to find out the correct equation. Okay, we also need to derive the Cartesian equation for normal. In this case, there's no trick, easy. So again, since the gradient of the tangent is x1 on 2a, so therefore the gradient of the normal would be 2a over x1. So equation of normal is y minus y1 equals to 2a on x1, x minus x1. Simple. My bad, I forgot the negative. Don't yell at me, Gemma. Oh, sorry, Gemma's not watching this. So x1y minus x1y1 equals to negative 2ax plus 2ax1. Okay, so they normally put all the variables together, put all the constant numbers together. So basically we got 2ax plus x1y equals to x1y1 plus 2ax1. Well, nobody can remember this, so I couldn't either. So don't bother, girls. Don't bother, girls. You don't actually need to remember any part of this equation, they'll either ask you to derive it or they will just give it to you. Maybe it's on the formula sheet, not 100% sure. Okay, so this is how we derive the Cartesian equation of a tangent and normal. So how do we normally use this? We kind of don't use this a lot because to find out the equation of the tangent, and they might ask you to actually use discriminant to find out what that is. Now, so for example, let's have a look what kind of question they can actually ask us. So example, now part A, let's write down the equation of a line such that the y-intercept is -2, something like that. Okay, so part B, hence find the equations of tangents to the parabola x squared equals to 2y with y-intercept -2. So that is actually not a quite complicated question. So what we do is we started with y equals to, now any equation, straight line with y-intercept of -2 can be said as mx minus 2 with each variable as a gradient as variable. And that's it. That's part A basically. So part B is we're going to solve this line and the parabola simultaneously to make a new simultaneous equation. The reason is, again, when they say tangent, basically means the line touched the parabola at one point only. That's highly related to the number of solution. In fact, discriminant. So we're going to solve y equals to mx minus 2 and y equals to, x squared equals 2y. Is that right? Yes. X squared equals 2y simultaneously. And therefore, we have x squared equals to 2 brackets mx minus 2. Tidy that up. X squared minus 2mx minus 4 equals to 0. Plus. And therefore, now discriminant equals to -2m all squared minus 4 times 1 times 4, and that gives us 4m squared minus 16. Okay, so now since the line is a tangent, therefore discriminant equals to 0. That is 4m squared minus 16 equals 0. Take it out, to cancel. M squared minus 4 equals 0. So m plus 2 and minus 2 equals 0. Therefore, m equals to 2 or m equals to -2. And we need to substitute back into the equation of this. Therefore, the equations of tangents are y equals to 2x minus 2 or y equals to -2x minus 2. They both can be tangent to the parabola x squared equals to 2y.